I will explain you theorem 6.2.3 in this video. So let us read the statement. If lambda 1, lambda 2, etc. lambda k in F. Okay, these are the scalars. Okay, usually scalars are the elements present inside the field F, right? So that is what here also we have. If lambda 1, lambda 2, etc. lambda k in F are distinct characteristic. These are the characteristic root here. Okay, for what they are characteristic root? For t belongs to A of V, this lambda 1, lambda 2, etc. lambda k in F are the characteristic roots. And if also they are given you some of the characteristic vectors of t, these are the characteristic vectors of t belonging to, that is, this v1 belongs to lambda 1, v2 belongs to lambda 2, etc. vk belongs to lambda k. That is what the meaning of this respectively, right? These characteristic vectors of t belonging to lambda 1, lambda 2, etc. lambda k respectively. Then we have to prove this. This v1, v2, etc. vk are linearly independent over F. That is what we have to prove. That is, in a finite dimension vector space, the characteristic roots are linearly independent. Sometimes if they ask you question from this to this, in the question paper, you should not feel like, oh my god, this question is I did not ever learn this theorem. You should not think like that. Okay, this statement can be asked like this also. Okay, so be prepared with both the statements. So here let us see the proof of this theorem. First you have to write what is given in the statement. So given these are the distinct characteristic root of t belongs to A of V, and also this is also given in the statement, right? So just copy it down. Now from this you can write this by using, I will show you the theorem also. By using this theorem, okay, by using this theorem you are writing this. What? You are writing this, okay? By using that theorem you can write like this. If these are the distinct characteristic root of t belongs to A of V, and these are the characteristic vectors of t belonging to this, then you can write like this. This v1 into t, this t is equal to lambda 1 v1, and v2 into the next v2 into this t is equal to lambda 2 v2. Like that you have to write till kth term. Okay. Now we have to prove these are linearly independent over F, right? So we are proving like this. Suppose they are linearly dependent. Like that you are proving. At the end you will bring the contradiction. So here you are writing like this. So if they are linearly dependent, then by the definition of linearly dependent, you can write like this. Alpha 1 v1 plus alpha 2 v2, etc. alpha k vk equal to 0, where this alpha 1, alpha 2, alpha k belongs to the field F, and not all of them are 0. Not all of these scalars are 0. Okay, that is from this to this, you are writing by the definition of linearly dependent. Now let us pass on to the next step. Now what you are writing is, by renumbering the vectors, you are renumbering the vectors. It means instead of, here what we have? Here we have what? Alpha 1 v1, alpha 2 v2, etc. alpha k vk, right? Equal to 0. Instead of this, you are writing like this. Renumbering the vectors. We assume this shortest relation to be. You are assuming like this is the shortest relation. That is how you are assuming. Okay. Is equal to 0, where beta 1 not equal to 0, beta 2 not equal to 0. You are assuming like this, and you are saying this is the shortest relation. At the end you will say you will get some other equation Yes, you will get some other equation, and that will be a shortest relation. That will be shortest than this. You will get like that. Okay. So you will say it is contradiction because you said this is shortest, right? But you are getting some other equation that is shortest than this, so you will get a contradiction. So like that you will finish the proof of this theorem. So here let us proceed. So after this step, what you are writing is you are multiplying with the t on both the sides of this equation, so that you will get, now you are multiplying, okay, so that you will get this. Now in the place of v1t, v2t, you can substitute a value, right? So here you have that. In the place of v1t, you are going to substitute lambda 1 v1. In the place of v2t, you are going to substitute this. In the place of vkt, you are going to substitute this. Like that you will do, so that you will get this term, get this equation. Okay, so now mark it as equation number 2 and mark this as equation number 1. Okay, so now what you will do is you are going to subtract 2 minus you will multiply lambda 1 with equation number 1, so that with that equation you will you will subtract that from equation number 2. Okay, so you will get this, and from this you are saying here lambda I minus lambda 1 not equal to 0 for I greater than 1, and beta I is also not equal to 0. So from this you will say beta I vi of lambda I minus, so here lambda I minus lambda 1 is not equal to 0 for I greater than 1. Okay, that is obvious, right? If I is greater than 1, then this cannot be equal to 0. If you cannot put 1 here, because you are saying that I greater than 1. So if you put lambda 2 minus lambda 1, you are not going to get 0. When you put lambda 3 minus lambda 1, you are not going to get 0, right? Only if the value of I equal to 1, then this will become 0. The possibility of getting equal to 0 is only when if the value of I equal to 1, right? So here you are saying that since this not equal to 0 for I greater than 1 and beta I also not equal to 0, how you are writing this beta I not equal to 0? Here in the assumption you are writing beta 1, beta 2, etc. beta g are not equal to 0. So from that you are saying here beta I is also not equal to 0. So if this is not equal to 0, beta I is not equal to 0, when you write the general term of this, when you multiply this to, you are not going to get 0, right? So that is what you are writing. So you are saying this is the shortest relation you are getting. This is the shortest relation. Okay, so this is a contradiction. Thus we produce this is the shortest relation than this. So here you are getting a contradiction. Therefore our assumption is wrong. Hence, what assumption is wrong? Here you have said, right, these are linearly dependent. This assumption is wrong. Therefore you get v1, v2, etc. vk are linearly independent over f. This is how you conclude the proof of this theorem. So here I have some confusions, and saying contradiction is also from this. Okay, this step is also little bit confusing to me. Okay, so when I get the clarity, surely I will upload it in a form of video. I will upload it. Okay.